Okay, so hello everyone. So for this week's Machine Learning Coffee seminar, this is a weekly seminar. We are meeting every week this same time. This week we have Jörg Tiedemann, who is going to talk about translation models. So this is going to be a very exciting talk. I'm looking forward to it. If you have any questions during the talk, can you write them in the chat, and I will then forward them to the speaker. Thank you. So Jörg, please.
Yes, thanks a lot for inviting me, and thanks for joining this morning session here. We managed just in time to actually get me connected, so let's see if I can manage to stay connected. Also, my connection seems to be a bit unstable. Sorry for that. What I want to try during that talk is to basically highlight a few things from a couple of papers, or 4 papers in general. So I would like to cover all of them. Let's see if I manage on time. But all of them are connected to looking at representations that can be learned by translation models, as we have a project going on where we try to look at representations that can be trained from parallel data, from multilingual data, and trying to see what kind of information is picked up by those models, and how can we actually analyze what is happening in those models. So, okay, just a little bit of background. So language technology, probably most of you know somehow about language technology, some more than others, but here just a picture to summarize again what we are looking at. We're looking at human languages, so languages that are used for communicating information and knowledge. And there's basically 2 things that we are concerned about, is understanding language and generating language. And both of them are connected to some kind of knowledge or meaning representation, something that we want to convey, some kind of information that we want to communicate. And now in language technology, of course, the idea is to replace humans doing this kind of act of communicating by intermediate, so having some kind of computational model doing that connection between humans and machines, or between machines and machines, doing some kind of natural language understanding and natural language generation in the same way as humans would do it. Now, what we have is, of course, a lot of data. So we communicate as humans and produce a lot of language, and this language can be observed like signals in text or in speech. But the interesting task is now to find out what is actually the meaning behind that text, or behind any signal that we can observe connected to language. So that we can understand what is happening, what is actually meant by this communication act, and how we can also generate language in a human-like way from some kind of meaning representations. So the interesting part is to find these latent spaces of meaning and finding models that can pick this up. Typically, we want to look at specific linguistic phenomena. So there's a lot of different things that we know about languages. There's different ways of expressing morphology. So word formation can be different in different languages. We have to know about these kind of word formations and how they are built. We have to know about syntactic structures and syntactic functions that sentences can take. And then if we go higher up in abstraction, we have a layer of semantics, so the meaning space behind some text or some kind of language input. Now, when we look at the current state of the art, where we have a lot of neural models building language models from data, then there's a new field that actually emerged because of the black box nature of these neural models. And BERT is one of these well-known models that have been really revolutionizing the field. We now have this task of actually analyzing and trying to find out what does such a BERT model or such a language model pick up from the data? What kind of linguistic information is actually taken from the data and represents things that we know about language? So this field is nowadays also called as BERTology, even though there's quite a lot of different language models around that have slightly different architectures, but are essentially based on the same ideas. What I would like to present is slightly different, not only language models, so trying to have a model that represents one particular language, but we would like to look at machine translation. And the motivation here is that if we look at this diagram representing those 2 different parts of understanding and generation, then machine translation basically combines natural language understanding and generation in a natural way, as we have some kind of source language that needs to be understood and analyzed, and then some target language that needs to be generated to represent the same kind of meaning. So here we have a nice way of including both of these tasks. We have an objective that we know about because we have a lot of translation data that we can actually observe. And we would like to see whether a translation model can pick up information that does some human understanding and also proper generation from that kind of understood representation that we learn. So this is the motivation behind the project that I'm presenting. We have a project that is called Fortran, Found in Translation. So that's the acronym for Found in Translation, where we basically want to explore how to build such translation models, and then to analyze and to apply them in different kinds of downstream applications. So if we look at the project setup, this is just still introduction. We have basically those different sub-projects that we are looking at. First of all, in the middle, we have the optimization and building of such models. So of course, we have to implement models that can do translation. And here we focus especially on multilingual approaches. So having something that is more than just between two languages. And I will come back to that later also in the presentation. And then we have projects that are looking at these models, trying to train them from different data sets, and then looking at applications. First of all, downstream applications that do some kind of extrinsic evaluation, looking at machine translation as such. So as we're training for machine translation, we would also like to see how well does such a model really perform on that task, and also transfer between different languages, for example. And here the idea is that we would like to see a very high level abstractions in between all kinds of languages and seeing whether there's some emerging neural interlingua coming up. And then we have other kinds of downstream tasks where we do inference task or reasoning over languages, and trying to see, for example, how question answering or natural language inference tasks would perform, where we need some semantic reasoning and would like to see whether we can get to some more human-like reasoning over language. And something that I'm looking at in this presentation mostly is the more intrinsic kind of analysis, so the interpretation of models that we learn. So on the top left corner, you see this interpretation sub-project, where we are basically interested in to see what these representations pick up from the data and how do they cover certain information that we are looking at. So this is our project that we are running and still will run for a few years to come. So because I don't really know about the background of people listening to this seminar, I also have a quick recap on natural language processing and how we use sequence models. So I do this very quickly just to also get to the actual papers. So I flip through this, those slides coming here quite quickly just to remind you about those models, and then if there's questions you can ask. So language essentially comes in most cases as some kind of stream information. So we have a stream of signals in a sequential way. Can be text or speech or other kinds of signals that come sequentially, and a natural way of representing such sequential data is of course a recurrent neural net that then reads through some kind of input from left to right or from the beginning to the end, and accumulates information similar to like humans would like listen to some spoken data and accumulate the information. So here we have just one example of there would be a recurrent neural network cell, and that would then accumulate information and building basically some kind of contextual representations or embeddings of the information read so far. So this is of course one of these typical structures, but then if you look at machine translation, we also have a generation component, which means that we not only have to read text, so somehow accumulating the information and understanding what is given, we also need to generate, and then we have the typical sequence-to-sequence model that has been proposed, especially for machine translation in the beginning, but now also for many other tasks. So where we take some kind of representation that we have accumulated, and then from that unfold that information and sequentially produce output from left to right. Often in many cases, there's also other models where you have a non-autoregressive method for producing something. So here we have still very basic structures. just for illustration, also single layer networks, where we just have one piece of information summarizing the entire sentence and then generating from that. And then, as most of you know, that a big push came actually from doing lots of other kinds of additional types of architectures, and one of the crucial things is to introduce attention, this attention mechanism that makes it possible to not only just summarize everything into one vector at the end, but instead of giving the decoder the possibility of looking back to the entire structure that the encoder is producing here at the bottom. So that you learn an attention mechanism that averages over all these positions from the encoder states, and then produces information that you can use in this left to right decoder steps to produce output with these contextual information that you get from the encoder. So this pushes the performance of such models quite a lot. And then on the bottom, you see also some other slight modification is that we also would like to have information that comes from different types of contexts. So in the beginning, I was looking at left to right models in these recurrent setups, but you can also have, of course, a bidirectional recurrent layer that does look in two directions and has then contextual information in both directions. So again, this is probably quite familiar to most of you. Then what we then also saw a big push came from the so-called transformer architecture, which then instead of having recurrent neural networks where you have recurrent steps going through sequentially through some information, you actually have self-attention layers that replace these recurrent connections and instead learn the connections between the different nodes in the sequence. Which means that we now have a very flexible structure. We can learn dependencies between all these different stages, make it a high capacity model with lots of parameters, but a lot of possibilities of picking up information that needs to be connected. And to make it even more complex, as we have now many layers, many connections, many parameters, we introduce multi-head attention, then basically allows every position to be connected several times to all other places in the sequence. For example, 8 different attention heads for each layer, making a lot of possibilities of connecting different types of structures, types of information from the sentence to each other, and building up a very complex network. So this is basically what we also will be looking at in this presentation. So as we have lots of parameters and the whole thing is trained end to end from lots of data, we are quite interested in what these parameters actually represent. So what is happening inside of such a box, and what kind of information do we pick up? So here we finally come to papers that I would like to discuss here. We had one paper that looked at transformer-based neural machine translation, which feels like it was a long time ago. It's only 2018, but nowadays it's called an ancient paper. So it was the first paper that looked at transformer-based neural machine translation, trying to analyze especially these attention patterns that we can observe in such models. So this was presented at a quite focused workshop, Black Box NLP. This is a series of workshops that really looks at the explanations of these black box neural models and trying to explain how NLP is working in such boxes. So to summarize that paper, we basically had the setup that we trained various translation models for different language combinations, always coming from English to other languages, also seeing what the different languages are influencing, what kind of influence they give into the information that is picked up. And we chose always to start with English as the most of the evaluation data that we could apply comes with English annotated data. So we can observe certain information and compare it to established knowledge in data sets that have annotations for English. So we trained those models and basically looked at different ways of interpreting and trying to figure out what the network is picking up, what kind of information. One thing you can do is visualizing. So visualization of, for example, these attention patterns. Another thing that we looked at is how can we induce trees from the attention weights that we learn. and compare that with established syntactic trees that you can see in annotated data for syntactically annotated gold standard data. And third task is probing tasks, which now is also very popular, where you have transfer learning of some pre-trained model and then you apply it to some downstream task by training a classifier on top of that or with that information. All right, so quickly giving you the results or some of the highlights. So visualization is a bit tricky, as you cannot really generalize that easily, but at least you have some visually nice information that you might get some intuition from. And what we observed is that these self-attention patterns in transformers, so where items connect to each other in a sentence, they look very sharp in many cases. And this is always happening also with the cross-lingual attention, that we actually get very sharp attention patterns where we have very focused regions inside of the structures. And here you can see four patterns that we saw a lot in the data that we observed. Of course, as I said, a bit difficult to make general conclusions, but we have seen that these kind of positional information becomes really important, that you look at always some kind of relative positions very strongly in local connection to the word that we are looking at. So the matrix that you see here is, well, the word to itself, the attention weight. Darker would be more attention weight and lighter would be less attention weight that the model picks up. So I will come back to those patterns also later, but let's look at some other results. So I go rather quickly through these things as I have a few papers to cover. Here we look at the syntactic information and structure basically that systems pick up. So for that we use the attention weights again. So we have these different weights of connecting items in a sentence, and then used an algorithm for inducing tree structures. So trees that connect tokens in a sentence, and wanted to see whether one of these attention heads, for example, resembles syntactic structure that we know of from linguistic theory, that we would have these kind of structures. So now the complication is that we have, of course, 8 attention heads. We have 6 layers in standard transformers that we are experimenting with. So those tables become quite big and messy. What you see here is just an excerpt of some of them. So layer, the first and the 6th layer, so first and the last layer of the encoder, and seeing all these different attention heads. How well do they perform when measuring what is called an unlabeled attachment score? So how well do they resemble the structure of a syntax tree that people have annotated in tree banks like this Cornell 2017 dataset? As we have many language pairs, you can also see that, of course, for different language pairs, we have different kinds of scores. What you can read from this table is basically that there's always one head that picks up more syntactic information, significantly more than others. So you can see some of these highlighted scores where you can see that one of those heads seems to pick up more of the syntactic information, and others focus on other kinds of knowledge structures that they try to represent in the encoding. So this is one takeaway from this. Another one is that it does not seem to be very specifically focused on one layer. It's basically spread over all layers. There's slight differences, but it's very difficult to make any conclusions here. Okay, I will come back to takeaways later also, so we can have more discussions if you like later. So for probing tasks, same as that, we produce lots of numbers. So what happens if you train, for example, a part of speech tagger or some semantic tagger on the encoder representations, then you can see that the performance, first of all, is actually doing quite well. So we have accuracies of quite decent values, not state of the art in that case, but it's not really the focus of this work. But you can see that in most cases we have over 90% accuracy, for example, in the part of speech tagging task, and also over 80% accuracy performance, for example, in semantic tagging tasks. Here the interesting part is probably to compare these different layers. as we wanted to know where exactly is that kind of information, the morphological information or the kind of word formation information and word class information seems to be more represented in the lower layers. Maybe also makes it intuitively quite clear why that should be. And then in the upper layers, you can see that semantic abstraction goes up. It is not maybe a clear-cut picture, but at least there's a tendency that seems to look like surface forms or information about surface information is more in the lower layers, whereas semantic information seems to be more present in the upper layers. Okay, this first paper, I think, triggered a lot of follow-up research also around the world. So there's quite a lot of interest in doing that. We had, this was kind of our first attempt of looking at that. You can see that these self-attentions, first of all, were interesting for us to see that they have very strong patterns and very strong focus, which is interesting. And I come back to that in the next paper. We also saw that syntactic structure is surprisingly little information is encoded in the representations, and it's kind of spread all over the place. So there seems to be not a very specific layer or specific place in networks where this is represented. And we saw that there seems to be a slight difference between lower and upper layers in terms of what kind of things they represent, whether they look more at the surface information and syntactic information, and whether they go more to semantics. Okay. Moving to the second paper, this builds quite a lot on the first paper in one direction, and here we pick up the ideas of looking at these attention patterns that seem to be very focused and seem to be very positional. So in some sense, there's a lot of discussion about how much are these networks actually over parameterized, and how much do we need all these parameters that are actually going into networks in the field. And we made experiments where we try to replace self-attention that has been learned from, that can be learned or trained from data with self-attention patterns that we basically predefine based on our observations that we have seen in the paper before. So we have observed that there's a lot of attention going to positional information or relative positions. So for example, looking at, for example, the same word or the previous word, the next word, or some very local context to the left or to the right. So we have here those 5 first patterns that look at this kind of local contextual information that comes just before and after the current word that we are looking at in the sequence. And then another strong focus that we also see in typical patterns is that there's always a lot of attention going to the end and the beginning of the sentence. Figuring out how like the information to the end is related to the end and the beginning of a sentence. We have 2 different ways of representing these fixed patterns. So they're now just predefined without making them trainable. And I didn't explain that there's typically also a way of dividing sequences into subvert units. And the reason for this is to have a fixed vocabulary that you are required for training such models. Intuitively, you would like to have something that is more a linguistic unit of some reasonable size, like a word. And that's why we also have these word-based fixed attention patterns that are basically the same, but only trying to then merge tokens that make complete words and trying to have the fixed attention patterns connected to the word as a unit instead of these subword tokens that you can also create. This is not very important, as the results that I show are more or less the same in the end. So we replaced attention patterns, attention parameters with these patterns, and then trained systems again. And here's some interesting results, and that was also surprising for us and actually influenced also others quite a lot. When you look at this, you can see in those tables here that these experiments showed that most of these fixed attention patterns work as well as trainable, learnable attention heads, or sometimes even better. So just walk you through some of these numbers here and the setups. So if you have settings that are called 8L, then this means that all attention heads in each layer will be learnable or trainable. So that would be the baseline. And then if you have the other lines, then you would have 7 fixed attention patterns, either on token or word level, and then just leave 1 trainable attention head to connect other kind of, to represent other kinds of dependencies. Still, so that left this in the picture to make that trainable. So 7F would be our 7 patterns and 1 trainable attention head. And then we compare this also to just leaving those away and having just 1 learnable attention head. And you can see that the baseline basically is more or less the same as what we can get with these fixed attention heads. So we have high resource scenarios and low resource scenarios, and you can expect that if you have something trainable, of course, you need a lot of data. And this German to English setup here is quite a decent setup with 11.5 million training sentences. And you can see that we still achieve more or less the same or even better performance from English to German with these fixed attention heads instead of having them all trainable. Maybe even more interesting is that if you go to low resource scenarios, then this kind of prior knowledge seems to really be beneficial, as we can see that we pick up information that improves the performance for translating between German and English in a small data set, and Korean to English, and English Vietnamese, and Vietnamese English. Okay, I feel like I'm doing not very well with time, as we should kind of finish up soon with the presentation. Let's see, I will not manage to present all papers, but let's skip the ablation studies. We can discuss that later. So this only tells you that all of these fixed attention patterns have some influence. They are important. So they have different kinds of importance. So you can see that the attention to previous and next words, for example, and especially previous context, is really important. And we did also some other studies on looking at what happens if you have all of the attention heads fixed and no trainable attention. Then you can see on the lower part of this plot here that the this test of figuring out a subject verb agreement that you need for some sentences is difficult to pick up for only those fixed patterns, as there can be long distances. So if the distance between those goes up, then intuitively, of course, you don't really have that information covered, and you would lose quite a lot of information by having only fixed positional local information represented. On the top, you can see that the decoder actually can compensate quite a lot for that information, and you would, even with only fixed attention patterns, you could get the same, more or less the same performance as with trainable ones. Okay, takeaways here are that so this was quite surprising for us and for many, that these very fixed simple attention patterns work as well as the trainable ones, and even better in low resource settings. So we could reduce the parameter footprint of those models, and we could even see a lot of benefits for low resource settings. And we could also show that these long distance dependencies are still difficult for those fixed attention patterns. So having one trainable one seems to be important. So now I'm not really sure what I should do. I have 2 more interesting papers to say. I could have one of them in 5 minutes and skip one.
So maybe, since there hasn't been any questions, so maybe if you can still talk like 10 minutes, and then we still have 5 minutes for any remaining questions.
Yeah.
That sounds okay.
All right.
But it seems that we right away have a question from Antti Honkela asking, how much did the number of parameters reduce?
I think it was around 8 to 10%. So I had the number somewhere. I wrote them down, but now I don't have them here. Let me see if I can find them. I believe it was something like 8 million parameters that we could skip. Let me see if I find that quickly.
No, that's good enough. Thanks.
Yeah. So it's substantial, but you know, there's still a lot of parameters left. Definitely. So should I go on?
Yes, please.
Yeah. So one thing that we also want to look at is whether we can disentangle or find linguistic information in these neural representations and see where are they, how can we measure them, and can we actually extract them from those representations. So this paper here looked at different ways of manipulating some or giving some data sets and seeing specific types of information that we can represent. So we have contrastive examples that represent active versus passive sentences. They basically explain the same, or they cover the same semantic information, but they just express it in a different way, different voice. So we have the different voice of saying something in an active voice or a passive voice, and then we have those examples, and we want to see how the representations look differently in the models that we train. And then we also wanted to see, for example, how negation is represented. So if you have the same sentence in an affirmative way and in a negated way, then what is different in those representations, and can we somehow figure out how this representation of that phenomenon is in those models. And we looked at BERT as a pre-trained language models, but we also looked at machine translation models in the second and the third row. So BERT is the top one here, and then we have two different kinds of translation models. So what we looked at is this, we actually applied so-called debiasing procedures. So debiasing is quite a popular idea of getting out different biases of these models. For example, gender bias could be extracted or could be removed from data, but instead we now want to see whether those kind of procedures could also be used for reducing the information about, for example, passive-active voice alternations or the negation information. Can we identify that kind of information in the models? And there's this procedure that has been proposed by Raffvogel and others, which basically does some kind of iterative procedure to reduce information in debias representations. We train a linear classifier that has some kind of weight matrix, and then we find node space to actually to remove the information, to project the representations in a way that this classifier would not work anymore. And then we iterate over those procedures to really remove more and more information based on that procedure of having a classifier first classifying that information, or while detecting that information, and then making it impossible for that classifier to do that kind of detection. And that surprisingly works well to really remove that information, as we can see in this picture here. So we have with multidimensional scaling those kind of figures on how well the representation has classified those different types of information, and you can see that the null space projection procedures really removes that information. And now in all those layers, in some layers we had very clear distinctions between the different parts. We could really identify them clearly, whereas after the cleaning, it basically disappears. So what takeaway from that is, first of all, that first these kind of null space projection procedure seems to work well. We can first of all see a very clear encoding of those active passive voice alternations. So that is clear in many layers, quite well visible in those visualizations here. And then we can also remove that, which means that there can be some kind of subspace that encodes that information, and we can even extract it. yeah, interest of time, just quickly here. So one thing is, of course, we would like to know whether this is very universal and generic. So can we actually also can we use the same kind of expected space in a different data set? So is this really global information that we expect? And then the picture becomes a bit more tricky. So here we have seen that that BERT, for example, as a language model, does not seem to make it possible to extract that information as some kind of global information that we can use for other data sets to extract the same kind of phenomenon from that data set. We have two different data sets that we looked at, one which is template-based generated synthetic data, and one is from an annotated crowdsourced data set. And it's maybe not that clear to see, but the upper parts from the dotted lines to the solid lines, there's almost no difference in how to classify this with the original data set and then with the clean data set. So it does not seem to work when you go to a different data set. Whereas if you look at the purple and light blue lines, which is representing the machine translation encoders, then there seems to be quite a change, and this seems to be transferable to a different data set. So we seem to have extracted that phenomenon from the information, from the representation, and can also remove it from a different data set. So it seems to be more stable. So that's the main takeaway from that picture. So here, takeaways again, syntactic and semantic information, like negation more semantic, or this kind of active-passive voice alternation more syntactic information can be identified and isolated from the representations. And we can extract that information from the representations. It actually transferred also to different data sets. So meaning that we can also argue that the phenomenon is really represented by that subspace that we have identified in the machine translation based encoders. Whereas for BERT, we have actually not seen that kind of ability. So we seem to have something that we can do of reducing information from the representations on that data set, but doesn't seem to be generic or general enough. So again, lots of open questions, but kind of interesting results. All right. Yeah, and I probably have to skip that paper. But I can also talk about this if there's no questions. Very quickly. Should I?
Well, yeah, it seems that we do not have any questions at this time.
I can also leave just space now. Okay, I go on. And just this one basic idea that we have in our project is that what happens if we add languages, so more languages into the model. And here again, motivation that if you have only bilingual models like translating from Danish to Swedish, you would not expect that the system is really forced to understand what is happening, as it's more mechanical. You can produce quite easily Swedish from Danish. You don't really think that the system needs to really learn understanding. Whereas if you have more distant languages, you might expect that would actually force it more to understand. And now the idea is that if you have really multilingual models, you would force a model to do some deeper understanding and getting closer to some meaning representations. And that's what this paper is trying to explore. Two models, one typical transformer model where you have shared parameters between all encoder and decoders, and you can have some labeling approach that makes it possible to use multilingual, to represent multilingual translation. I don't go into the details. And we have a second model. We have a so-called attention bridge, which means that we have various encoders that are language specific and decoders that are language specific, but we connect them with a shared layer in the middle that represents the intermediate representation that everything has to go through. So, and we hope that this kind of intermediate representation would be a very abstract language agnostic layer. So we implemented that kind of model. And then we experimented with multilingual models with different settings. So just bilingual models where you have only one target language. Then you have trilingual models where you have 2 target languages, and then 3 target languages, 4 target languages, 5 target languages, and we always come from English because we want to look at the English encoder, what is happening with this encoder. All right. Yeah, quickly jumping to results, and so there's something that you can do with linguistic probing tasks, basically trying to find out what kind of linguistic information is picked up by those models by classifying certain probing tasks on top of the representations. And here you see for the transformer model that has all parameters shared, all these different tasks, and you can see that in this picture you actually don't see any significant difference besides of this word content task, which is a weird task that actually has the opposite behavior from, well, has a behavior that can be explained, but doesn't really is interesting in this way of analyzing the models. You have on the x-axis different numbers of languages that we throw in, so 1 to 5, and then we see accuracy numbers of predicting these downstream probing tasks. And we can see that there's a little bit of fluctuation, but not a clear picture. So our intuition was kind of wrong. Nothing really happens if you throw in more languages. The interesting part is that if you use this kind of attention bridge model, so with this intermediate representation, then this becomes a bit more interesting. As you see, in most of those cases, you have a clear tendency of going up. So now these tasks are, of course, kind of testing different kinds of aspects of linguistic representations, but you can see that most of these tasks have a clear upgoing tendencies if you throw in more languages, getting a better prediction, so somehow getting better representations of the linguistic information on certain types of linguistic information without giving it more English data to train on. So the English data is always the same, but we only change the translation part. Meaning that we have a more difficult task for a machine translation model to learn from all these languages, and this pushes the model into a more abstract representation that seems to be interesting patterns that we can observe here. So I need to end. So this is the takeaways from that paper. So this multilingual bridge model seems to really do what we expect it to do. So our model seems to pick up that kind of additional information from multilingual input. Whereas in the transformer models, it seems to create different language subspaces, but doesn't really make this push of one generic language agnostic representation that we would expect. So our intermediate representation seems to be better for this kind of purpose, which we then also would like to explore more in the future. So sorry, I should not have all these papers. So these kind of conclusions we have so far. Just to summarize, quite little syntactic structure so far we have seen. There's many follow-up papers that discuss from different angles these kind of how much syntax and linguistic information is picked up by encoders. So far, I would still argue it's quite little syntactic structure, except of when you really force it to do this kind of syntactic information that you would like to extract. And then also more intuitively, you can really see this information is proceeding from more surface-oriented information on the lower levels to more semantic information on higher levels, which makes kind of intuitive sense, and but nice to also see this, those patterns popping up from the models. And then interesting was this that we can prune networks quite a lot by for example, using predefined information, positional information that we see a lot, so we can have consistent patterns that replace trainable parameters. So yeah, I think I should stop here, and just thanks also those two people who actually did most of the work that I presented here. So Hande and Alessandro, they were the main authors of those papers, and they have been doing all the work. And with this, I thank you for your attention, and I can take questions and stay a bit longer also. Thank you.
Okay, thanks, Jörg, for the very interesting talk. I think we still have time for one or two quick questions. So yes, I think we have